Welcome. This is a deep learning experiment comparing 4 ML approaches. Part 1 checks training from scratch and transfer learning. Part 2 checks direct and indirect training data. Let's start part 1. The goal of comparing training from scratch and transfer learning is to understand their pros and cons. Training from scratch means training a brand new neural network with random weights. Transfer learning means using a neural network already trained on big data sets and fine-tuning it or using it to get features. In ML, choosing between these is common. I want to compare the speed, ease, and compute cost of both. The face emotion computer vision dataset is from RoboFlow. It has 7 emotions and 5,000 images, which isn't a lot. It's split into 3,500 trained, 1,000 valid, and 500 test. Given the domain gap of ImageNet and this task, fine-tuning will be necessary. First, I will train 3 versions of our custom network, EmotionNet. Then, I will train ResNet 18 followed by ResNet 50. I chose ResNet because their architectures are well regarded in computer vision, known for their strong performance. ResNet models were trained on ImageNet and are easily accessible on PyTorch. Imports can be broken down into standard library, data handling and visualization, machine learning, and local imports. MPS is available on my MacBook M3 Pro to accelerate PyTorch training. For reference, 1 hour on CPU takes 10 minutes. The images were augmented with cropping, flipping, rotating, and color jittering. This makes networks insensitive to these transformations. These transformations are only done to training samples because when we test the model, we want to see how well it does on unaltered data. Let's start with EmotionNet. EmotionNet combines local and global features into a layer, which is then flattened and fed to a classifier which makes a prediction. Using OOP in PyTorch, the model is easy to understand. Local feature pathway has smaller kernels to focus on detailed information, while global looks at the overall expression. We get a simple model with many parameters. The loss and accuracy graph over epochs show early convergence and signs of overfitting. 10 test image samples show that EmotionNet is not performant. It predicted happiness a lot, maybe since happiness is the majority class. Left confusion matrix belong to our EmotionNet, and right represents the ideal. EmotionNet seems to always predict happiness, causing poor performance. EmotionNet has overfitted. We can use regularization techniques like batch normalization and pooling. Huge model size means we have to redesign a more efficient architecture with less parameters and more efficient layers. Cross-pathway attention lets local and global feature pathways interact and influence each other. For example, the global pathway could guide the local pathway to focus on the relevant local features and vice versa. Self-attention weighs the importance of different parts of the input. For example, self-attention can help the model look at the most emotionally relevant features of the face. These improvements would be what we are striving for in EmotionNet v2. EmotionNet v2 is more complex. First, the residual block helps with overfitting and efficiency. Second, the self-attention module is used for attention mechanisms in different parts of the network. Lastly, we'll learn about the other layers and see how they are initialized. The residual block allows the network to go deeper without the vanishing gradient problem, similar to the batch normalization. This is more efficient because we can go deeper rather than wider. Self-attention uses the QKV as the 3 convolutional layers to turn the input feature map into QKV representations so that we can calculate an attention map with the dot product between QK, followed by a softmax operation. The attention map weighs V, letting it focus on important parts. The output is scaled by the learnable parameter gamma. We start with 0 so it can gradually learn to incorporate attention. You may not see convolutional layers in the local and global pathways, but they're actually within the residual block. These residual block layers extract local and global features. Max Pool 2D reduces spatial dimensions, and self-attention can weigh features. While the design is exactly the same between local and global, this is more of a goal and not enforced. What's more important is that both pathways learn different sets of features, and even if they start similarly, the optimization process will push them to specialize in different aspects of the input. The cross-pathway attention weighs the local features in context of global features, and vice versa, leading to a more integrated representation. The fusion module prepares the combined features for classification, with a residual block to further process them, self-attention to weigh the features afterwards, and an adaptive average pool 2D to reduce the dimensions to a single value, producing a feature vector. We also have a dropout 2D to prevent overfitting. Finally, the classifier maps the feature vector to the emotion class. The result is a deeper model, but with much less parameters. The loss and accuracy graph shows that the validation score is higher than training, which is desired. The model is no longer always predicting happiness. However, we can see that the model still predicts happiness quite frequently, which leaves much to be desired. The benchmark shows much smaller size and slightly lower inference time, so it's more cheaper to run. However, we see higher performance. One last optimization we can make is to create an even smaller model with faster inference time. We can combine concepts from V1 and V2 to generate V3. EmotionNet V3 starts with shared features to save space. Local and global blocks are inspired by V1 and uses smaller and larger kernels respectively. Instead of self-attention, we have channel and spatial attention focusing on channel and spatial-wise feature importance. The final layers are simpler and uses a conv2d block with a basic classifier. The model did worse than V2, but it is smaller and faster. To sum up, less is more, and a good design can sometimes outperform more parameters. On to transfer learning. Look at how easy transfer learning is. These two lines are all that is needed to initialize the model. The loss and accuracy graph shows slight overfitting. However, the accuracy graph shows that our model has hit 60%, reaching predictive values that we have never seen before. The sample shows a huge jump in accuracy, scoring 7 out of 10. The misclassified images seem rather debatable too, even to the human eye. We can see a beautiful diagonal line that matches the ideal confusion matrix. Even with double accuracy and more parameters, the inference time is much lesser than EmotionNet V3. This is because of the highly computationally efficient optimizations made in the ResNet architecture. There might also be some library level optimizations in PyTorch that weren't applied on custom trained models. This proves that a model with more parameters may not be slower to infer, because the operations and computational cost per parameter may differ. ResNet 50 is like ResNet 18, but instead of 18 layers, it has 50, giving it higher predictive power. Surprisingly, it's not that accurate. The matrix shows that it misclassifies sadness as anger, fear as surprise, and though these emotions may look similar, it has underperformed ResNet 18. I would say that the primary reason it underperformed is the small dataset, which provides difficulty for deeper networks to converge to good performance levels. In short, with carefully designed custom architectures, we can achieve good performance with fewer parameters and smaller model size. However, in the case where we have little data, transfer learning is the best. ResNet 18 doubles the accuracy and efficiency, and this small dataset severely limits the use case of fine-tuning a deeper pre-trained model like the ResNet 50. On to part 2. First, let's define our new dataset. It's a dataset of reviews of drugs, and in it, we have ratings by the reviewers on the drugs. Our goal is to predict sentiment from the reviews, and the ratings will be our output variable. Direct and indirect training means that while we test both of the generated models on the drug review test data, indirect will be trained on another training dataset instead of drug review trained, for example, IMDb reviews. For this experiment, we will not only have an equivalent model architecture of training from scratch for both sides, but also a transfer learning component. This will bring more insights into how direct and indirect training affects these approaches. We import similar libraries to part 1, but with the change from ResNet to AutoModel, allowing us to import MiniLM, an encoder transformer model that is smaller than even DistilBERT yet with good performance. Our correlation matrix of the training data shows that all columns exhibit weak correlations with each other except for useful count and ratings. The useful count shouldn't be included because it appears together with ratings. Therefore, in cases where you need ratings, you probably wouldn't have useful count as well. Our imbalanced class distribution across ratings means that we have to include class weights that adjust our criterion. For more alternative dataset options for our indirect training, we need to bin our values into negative and positive sentiment. To do so, I've read the sample reviews and came up with the splitting threshold of between 6 to 7. This is because at ratings 1 to 6, there is a strong focus on the negative impacts of the drugs, whereas at ratings 7 to 10, even though there may be some initial side effects, they emphasize more on the drug's treatment effectiveness. After some basic pre-processing and data splitting sorted by date to better reflect its real-world utility, we train our direct training transfer learning, which shows a large amount of overfitting. Our custom model is a bidirectional LSTM-based neural network for sentiment classification. It starts by embedding words into dense vectors, processing these embeddings using a bidirectional LSTM to capture sequential context, and then uses fully connected layers to classify the sentiment based on the LSTM's output. Even larger amounts of overfitting are seen. Overfitting is a more common phenomenon compared to structured data, since text data is much more complex, especially with LSTM-based networks. If you recall, the previous graph showed that the pre-trained model overfitted the more epochs there were. Thus, it's interesting to see that the model initialized from random immediately had a big gap between training and validation metrics. We can see that our pre-trained model was also overfitted. However, our model from scratch, although with graphs that can be considered as overfitting, has by far the least overfitting. One additional reason our models could be overfitting was also the sort by date decision. If it is true, that means that the ratings of the reviews may somewhat be correlated with some temporal function. Product quality increasing versus decreasing over time, external events like a certain disease being more common, and so on. Saying this, we have learned a new potential factor. However, we should still keep the current configuration because in production, our models will always be predicting on future data, and our date-based splitting will give us a more honest assessment of how our model performs. Our model comparison shows that the direct transformer achieved the highest performance across all metrics. This is highly expected since pre-trained models are often more optimized for common tasks like sentiment classification and have been trained on large data. Indirect pre-trained models achieve good performance, and seeing that transfer learning outperformed training from scratch, it makes sense that transfer learning is the best option. Direct model performed just above random chance, with a significant drop of precision. indirect custom model performed worse than random chance, indicating that the indirect data probably gave it contradicting insights and lured it against the wrong option. With this, it can be concluded that direct training consistently outperforms indirect training. While it's possible not to have access to the domain-specific data due to resource constraints, direct training is still the optimal solution for production systems. And if possible, always experiment with transfer learning because it is highly performant and easily trainable.